Good afternoon. Welcome to a new episode of SimCenter TV broadcast. Today we're streaming out of Boston, Massachusetts. My name is Philipp Mucha and I'm a computational fluid dynamics engineer in the post-sales organization with Siemens Digital Industries Software. The title of today's talk is Ship Maneuvering Prediction Using SimCenter StarCCM+. The goal of the talk is more or less to provide a high-level overview of established and reliable maneuvering prediction methods against the background of resources, cost constraints, design objectives, and resulting fidelity requirements. Then I also want to highlight the possibilities and the value of interconnected simulations across the entire SimCenter software portfolio for ship maneuvering, standard applications, and more advanced and complex scenarios. The agenda of the talk is quite straightforward. We'll start with an introduction to put the topic into context of industry and science and basically a software context. Then we'll talk about modeling requirements. What are the important hydrodynamics of ship maneuvering that have to be considered when choosing the right approach? This leads us to the distinguishing of two dominant methods, which will be the indirect maneuvering prediction method and the direct maneuvering prediction method. Then we'll talk about the aforementioned unconventional applications and interconnected simulations. And last but not least, I want to underscore some facilitating numerical techniques that SimCenter StarCCM+ has to offer to cater to all of these tasks that we'll deal with beforehand. So if we look at ship maneuvering prediction, we can definitely see an uptick in the interest in this topic over the past, I would say, almost 10 years. So why is that? The first point is the increase in ship dimensions. Let's take a look at container ships. So if we look at the Panamax class of 1980 with 3,500 TEU, and then take that all the way to 2013 when the EEE class with close to 20,000 TEU came about, we'll definitely have the challenge that not only aren't we per se familiar with the change in maneuvering behavior going from a 200-meter long vessel to close to 400-meter long vessel, we also need to incorporate that into the integrated design approach, because changes in the hull that come from meeting maneuvering criteria apparently also influence some other important aspects. Second, green shipping. So the introduction of regulations to limit exhaust gas and greenhouse gas emissions led to an overall decrease in power installation. So decreasing power on a ship brings to the attention in the context of maneuvering if the vessel will still be able to meet the maneuverability criteria in adverse conditions like a storm, waves, wind, or in shallow water. Because apparently with less power, that is a direct concern to the ability to change or keep a course or make a turning or stopping maneuver or attain a certain speed. Then in the context of growing ship dimensions, we have to think about harbor approach and departure phases. So the majority will, for a container ship of the time, will be spent on the open ocean, but actually the accidents and the maneuvering is important in the harbor approach phases. So under keel clearance management is also of big concern, and maneuverability in tight spaces. Then talking about tight spaces and potential accidents, more and more do litigation processes and infrastructure design processes rely on simulation technology, because it has advanced considerably since the 60s and 70s. So this finds its way into court processes, or also with hydraulic engineering and construction design specifications. So apparently underlying our maneuvering models. So it's important to spot the right fidelity here, because infrastructure is very expensive. So if you have a better understanding of the ship motion behavior, then that leads to better infrastructure. And last but not least, I put smart shipping. So with technology evolving, digitalization evolving, and also trust in autonomous transportation. So for example, in the automotive industry, but also in the shipping industry, we have to talk about the models that these control algorithms rely on. And that is inevitably a mathematical maneuvering modeling problem. So whatever we can learn from computational fluid dynamics will also be beneficial to this megatrend of smart shipping. Let's quickly recap what maneuverability analysis really concerns. So by ship maneuverability, we refer to the dynamic response characteristics of a ship to commanded changes in direction of travel or speed through their control surfaces. Conventional control surfaces would be rudders, propellers, and fins. Bow and stern thrusters, as well as pod-driven thrusters, would represent unconventional maneuvering devices. We usually rate maneuverability by the cost employed to meet certain requirements. For example, the time to complete a maneuver, course, lane, or speed changing and keeping, as well as positioning, and the applied control effort or change of forward speed in response to this maneuver. Let's talk a little bit about the hydrodynamics, because that is central to picking the right approach with SimCenter Star CCM Plus to do maneuverability analysis. So at first, we have to study the equations of motion. So that comes from Newton. This is here formulated for all 6 degrees of freedom. And we directly see here, indicated by the red color, where the trouble arises for the hydrodynamicists. So what is not known is how to express the external forces and moments. Apparently in maneuvering, we have to deal with and address an array of force contributions. So there will be force contributions from the hull itself, the resistance to forward motion, to sway and yaw motion. There will be contributions that are proportional to acceleration, and then there will be contributions that will be proportional to velocity. And then, of course, the hull interacts with the propeller and the rudder. So it's a very complex physical scenario and phenomena that we have to model. So let's make our lives easy and just resort to Navier-Stokes. So basically, we will build a CFD model of the ship in a finite domain and specify rudder and propeller action, and then we'll get the motion responses and all the other sought after metrics from CFD. Very convenient. Unfortunately, we don't always have the resources and the time to do such an analysis, and sometimes it is not required to go into fidelity levels at the highest level. So then we can say, let's see or look upon the moving ship as a mass spring damper system and say that hydrodynamic forces are a function of the state. So that would be the motion amplitudes, velocities and accelerations, and then the inputs, rudder angle, RPM, whatever is an input to maneuvering. Oftentimes, when we talk about the hard maneuverability criteria of IMO, we're not interested in certain degrees of freedom, modes of motion. So we can break this down to the horizontal modes of motion only. So that the task would be to model X, Y, and N. So let's go back to the direct maneuvering simulation. So as I mentioned, this draws upon the numerical solution of the Navier-Stokes equations. Most often this will be based on Reynolds average Navier-Stokes equations. And basically this will feature a full-on modeling of the ship and its appendages, as you can see here in the lower left-hand side picture. And usually the global motion domain, a global domain motion approach is invoked, as opposed to modeling a large part of the ocean or sea that the maneuvering takes place. And then appropriate boundary conditions and other settings are are being invoked. Unfortunately, this comes at quite a cost, which we will address later, and we'll try to elaborate when it's actually required to go to these lengths and what would favor the choice of this highest fidelity model. Let's summarize the pros and cons real quick before we discuss the indirect maneuvering simulation. So this is basically the best known hydrodynamic model, and there's no modeling effort outside of the task to set up the CFD simulation. Another advantage is that we can simulate any maneuver, including many additional effects. So if you have tanks inside the ship where sloshing plays a role, on the roll motion, if that is included in a Fordorf model, wind, waves, shallow water, or varying sea topography, everything can be considered. And besides the motion responses, we have access to an extensive data of the flow fields, pressure distribution on the hull, waves around the ship, segmented forces. If you want to study the lifting flow configuration or situation, we can study where exactly the pressure centroid is in different maneuvers. We can look at rudder forces in depth at every time step, and we can study rudder propulsor hull interaction, and also scale effects if required, if not run in full scale, but in model scale. The disadvantage of this method is basically cost, and there's 3 sub-items that arise from this general cost disadvantage. So for maneuvering, there's a large disparity between different time scales. So let's take the example of full-scale investigations. So usually we are well equipped with a time step of 0.1 seconds to resolve global ship motions in maneuvering. However, propeller motions are the limiting factor here. So if we have, well, depending on the propeller model chosen, we need to choose a time step that corresponds to 2 to 4 degrees of propeller rotation per time step. So that's a couple of orders magnitude lower than global ship motions. But this would set the time step and the cost implications ultimately. And in the end, even if we can afford to run a direct maneuvering simulation with this model, then if we have the task to arrive at a design envelope or explore a huge design space, that becomes infeasible pretty quickly. So let's look at indirect maneuvering prediction and how CFD and Syntastasis Sim+ in particular can be leveraged for this task. So first of all, I want to recall the simplified model of the mass spring damper system. So in the horizontal plane, there are no restoring forces or moments, so the spring element vanishes. So then we have a damper and mass or mass damper system. So here, as I said, X would represent the state variables, and then U would be referring to any input. So the first task basically would be to arrive at a formulation for the external forces that would keep us within the realm of the differential equations that Newton's equations of motion constitute. And they can then be solved within seconds, and arbitrary rudder maneuvers at the same operational point can be looked upon. So usually to come up with a model like this, a decomposition of force effects is being done. So there will be forces coming from the motion itself, and that would affect the hull. Then there's rudder forces, propulsion forces, and one can keep them modular, or one can lump them all into one force term basically, and express the hydrodynamic forces and moments through multivariate polynomials. So if we look upon the inertial force contributions, the damping force contributions, and the rudder force contributions at the very top equation here, we can say that, for example, the response of the sway force in response to a deflection or displacement in sway, if we have a sway velocity that follows a polynomial of third order, so that would look like the second equation from the top here. And what is unknown is, or what is unknown here are the red marked coefficients. So I would like to call them hydrodynamic or maneuvering coefficients in what follows. In the literature, in the field, they're sometimes referred to hydrodynamic derivatives, whereas the linear contribution would be the linear derivative, and the coefficient acting on v to the power of 3 would be the nonlinear derivative. Found that pretty imprecise because derivative by definition is a linear operator. So let's just call them maneuvering coefficients in what follows. These are unknown. We have to find these to be able to solve the mathematical model. A very widespread and established model follows the one that is appearing here in the box. And apparently you can see here there's contributions that are functions of the state variables, but we also see quite a bit of or quite a few of cross-coupling terms. And they represent a challenge in terms of parameter identification, because we would have to run tests on idealized trajectories that would basically vary at a time both of the terms that appear in the coupling. So that makes the test matrix for parameter identification very large. So the question is, do we really need all these cross-coupling terms, or can we come up with a reduced order model? So that would reduce the cost of our CFD campaign to resemble the captive maneuvering tests for parameter identification. So here, just from a publication that is referenced here, you can see, and this is just an X curve. There's many more chip types and many more maneuvers that will run. Basically, this model has been validated thoroughly and is proven to be very good. So the first step in reducing the model and thereby the CFD PMM campaign, planar motion mechanism, is basically to do a sensitivity study. So every coefficient in the model was perturbed by a factor of 1.2, and then the response in the tactical diameter of a turning maneuver was measured. And it was found that basically the most important coefficients are the ones that are shown in the top figure here. So if you vary these coefficients, you'll get a response in a tactical diameter that is above 10%. So all the other coefficients didn't really respond to that. It's a very pragmatic approach to look into a model reduction, but it works in terms of the results that are obtained. To take this to another level, one can also plot the instantaneous hydrodynamic forces on the ship. And one can see that on the left-hand side, these are really the important contributions. You see here the force in response to sway velocity, yaw velocity, and so forth. And on the right-hand side, you can see some of these cross-coupling terms here. They really come in with an order of magnitude less during the steady turning behavior. So they might not be needed because they're not affecting the equilibrium of forces in steady turning. So in the end, a reduced model can be derived, which looks somewhat like that. And I would consider that to be the very, very bare essential maneuvering model based on multivariate polynomials. So the coefficients you see here in red, these are the ones that we have to identify using STAS-CCM+. So STAS-CCM+ comes conveniently with an inbuilt module for captive tests on idealized trajectories. So we have, you can easily set up pure sway, pure yaw motion tests, rotating arm tests with drift, or a sweep of the drift angle. And that's all available through the DFBI module and the DFBI body motion option planar motion carriage. What are the pros and cons of this approach versus direct maneuvering simulation? So we have a fast and efficient parameter identification because we can automate all these sweeps that are required to explore the force responses to different yaw rates, different drift angles, and so forth. The hydrodynamic coefficients that we derive already include the effects of the free surface, if modeled, viscosity, rudder, propeller, hull interaction, and so forth. And once the mathematical model is identified, arbitrary rudder maneuvers can be simulated based on the operational point, which is the forward speed, the approach speed to the maneuver that was underlying. When using modular mathematical models, so not lumping everything into multivariate polynomials, but really have a separate rudder model, separate hull model, and so forth, we have great flexibility for modifying an existing model and model components by introduction of enhancements. So we already have a model, and now we equip our ship with a bow thruster. So I just have to run some parameter identification test to get the module for the bow thruster, and I just plug it in. The cons are the additional modeling effort. So what is the right mathematical model to choose? Then the parameter identification, which you also find on the pros. But what I mean here as a con is basically you'll have to have an environment to do the curve fitting and solve the regression problem based on the test results to link them to the mathematical model. Unless a large model valid for all 4 quadrants of ship operation is used, these models are, the one that I showed is only valid for 1 operational point. So fixed approach speed, fixed RPM. So I can run any rudder angle, I do different turning maneuvers, but I can't go and maneuver model half of the forward speed or double the forward speed with the same model. So one other disadvantage is that there's a huge modeling effort when this should be extended to unconventional situations like waves or shallow water. Okay, let's walk through an example for indirect maneuvering prediction using StarCCM+. So the case here is a deep water KVL CC2 tanker at 15 knots, rather low fruit number of 0.1. So the first simplification that we can make is to eliminate the modeling of the free surface. The methodology, though, is relevant for both. The cost just changes slightly in running because the grid apparently has more control volumes when run with the free surface considered. We're going to be looking at a hard rudder turning maneuver, and that would, for a tanker, not happen anyways at very high speeds. So that's a reasonable speed and assumption to make. On the left-hand side, you can see the test campaign. So in StarCCM+, we perform resistance tests. On the right-hand side, you can see the ranges that these sweeps take. Rudder tests by steady forward motion, varying the rudder angle and computing side force, yaw moment, and resistance, and then linking that to the mathematical model, getting the coefficients. In analogy, drift test, turning test, pure sway, pure yaw, and then drift and yaw tests. So this was the grid that was being used. The virtual disk was applied because there's no requirement here for this low forward speed, and the maneuver we look at to accurately resolve the propeller flow. We just need the wash over the rudder, basically, which the virtual disk can provide. And that's completely in line with the fidelity level that we sport anyways in indirect maneuvering prediction method. And then a grid sensitivity study for a drift test at 12 degrees was performed, and the sensitivity to spatial discretization was very weak. So the second causes grid of around 1 million cells was used for all of the tests. You can see here the maximum difference to experiment was 6.8%. So then we won all these tests, resistance tests. You can see here results compared from CFD to HRMI experiment that's taken from the CIMAN workshops, so publicly available data for the experimental side. Rudder tests on the bottom. Then the same is done for drift and yaw. There were no rotating arm tests from the experiment available, so that's why you don't see experimental data here. But agreement is, as expected, CFD has already been shown to be able to resemble captive model tests fairly accurate, so no surprises here. And this is a pure sway and pure yaw, because we need the YV dot, NV dot, basically acceleration related coefficients. So finally, upon application of regression analysis, we arrive at a fully populated mathematical model. So these are the coefficients here. So that's very much reduced compared to the original model that I've shown. And these are the results if you solve the equations of motion. Hard rudder turning maneuver of 35 degrees rudder angle to port and starboard. You can see here that the simulation results are in fairly good agreement. The maximum deviation is for the starboard turn to starboard advance of 11%. luckily, we also had uncertainty analysis from the experiments. They were conducted at MERIN, also available through the Simon workshop. So that is within reasonable levels, especially considering the, let's say, simplicity of the underlying model. Now, let's look at the trajectories are well and good, but we also need to look at the state variables. So drop in forward speed for both turn to port and turn to starboard were in very good agreement. So was the drift angle and the yaw rate. Now let's look at the overall cost and employed resources. So a medium resolution grid was used, around 1.3 million cells. Convergence for each of these steady tests, so steady drift or steady turning, was on average reached after 400 iterations. So that's a steady simulation and 15 minutes computing time. The strategy for parallelization was 50,000 cells per core, and 24 cores were employed for each test. So the static test, so totality to enable the regression analysis number was 35. And if you have only 24 cores available, then that is done in 9 hours. If you have more available, apparently you can split that and get there even faster. Dynamic test required 20 minutes per oscillation period. So usually you need 3 or 4 periods to be able to do the Fourier analysis to derive the coefficients. The 6 tests that were done were completed in 6 hours. So overall, 15 hours if I only have 24 cores to get the entire set of coefficients. And seconds later, I have results of any rudder maneuver simulation based on the given operational point. So if we have to include the free surface, these numbers will apparently increase. But I think one can fairly say that we'll get a grid maybe around 3 or 4 million cells, and then the 15 hours may translate to a day and a half or something like this on the same with the same computational resources. So very reasonable and efficient if you look at that you will get the entire envelope of turning maneuvers, for example. Now, what tools are there in StarCCM Plus to efficiently do this and not set up all these 35 or however many tests one by one? So since version 2019.1, we have simulation operations as basically an alternative to Java macros. And if we were looking at a steady drift test, basically what we'll have to do is set up one baseline simulation, mesh, solve, and then we have a convergence criterion for the force, and then we'll enter a loop where we say we update the PMM property, so that can be the drift angle, the yaw rate, or combination of both, then rotate either the overset mesh or remesh the entire domain, then solve again, stop when converge, and loop through this until the sweep of the drift angle, for example, is done. And then move to the next PMM test. So this can all be automated. So this is a really simple example here. So this is zero drift configuration on a small sailboat. Forces are very small in the site and the zero drift configuration. And now once the convergence criterion is met, we'll switch to the next drift angle, remesh, run, and basically we'll get this iteration force history here, which we can then use for the regression analysis. One thing that I want to highlight before we move on to the direct CFD simulations is basically choosing the method, choosing the approach, and saving costs. Sometimes if I just want to do a quick check for maneuverability for different hull configurations, I don't need a full-blown nonlinear maneuvering model. I can resort to linear equations of motions as shown here in state variable representation. And I can do a core stability check. So basically, the mathematical model is the same as the one that I showed. We're just looking at the linear contributions only. So if you do a stability analysis in classic system dynamic sense, you can turn to the characteristic polynomials, evaluate the eigenvalues, and you'll plug in the hydrodynamic coefficients, and you quickly find out that it basically boils down to the criterion here in the green box, which is LR, core stability is therefore for LR greater than LV. And that basically refers to the lever arms in response to turning as opposed to drifting. So LR has to be greater than LV. And what you see is, because we know the mass, the longitudinal center of mass and the forward speed, all we need is the linear coefficients with respect to the sway force and yaw moment and V and R. So in order to do that, we just need 3 tests, 3 drift tests and 3 turning tests. And that I can achieve in less than an hour with aforementioned resources. So in less than an hour, I can check if I, with a very sophisticated flow model that Rand's equations represent, I can check core stability for one hull shape. So overnight, I can maybe run 8 of these. Let's go to direct maneuvering simulation. So first of all, in what follows, the results that are being presented here were kindly provided by the Institute of Ship Technology and Ocean Engineering at the University of Duisburg-Essen. And the paper that is underlying to these results is referenced here on the left-hand side. And we will be looking at direct CFD simulation of maneuvering for a dock ship. So it's a twin screw ship with spade rudders, roughly 100 meters long. You can see the main particulars in the table here. So right off the bat, a hard rudder turning maneuver of a 35 degrees rudder angle basically yielded these results. And I throw this at the audience here right off the gate because it basically underscores that the direct simulation of maneuvering based on Rand's equations is the best known model and has the least risk of basically not meeting the accuracy requirements when we compare to measurements, if the measurements were or field sea trials were done correctly. So both advance and transfer and the trajectories were fairly spot on, and the drop in forward speed as well. Yaw rate and drift angle were in a similar difference or magnitude of difference than you can see for this here. So apparently we need to talk about costs, because we don't need to do all the modeling and parameter identification effort if we can resort to something as great as this. But what is the actual cost involved, and what are the little nuances that we have to consider when doing direct CFD maneuvering simulation? So let's look at the inference of propeller modeling. So what was done here in this investigation is to look at both modeling the propeller by a moving reference frame. So geometrically, the propeller is modeled in both approaches, but in the moving reference frame, the propeller region, which is this yellow cylinder region that you can see here for both of the propellers, the propeller itself didn't rotate, but a moving reference frame was invoked inside this region. And then the sliding interface method was also invoked, and the results were compared. So at this point, what we have to take away here is there are differences. So where do these differences emerge from? So if we look at the side force on one propeller blade, we can see here that the moving reference frame basically does not give any asymmetry in the force history, because apparently this is an idealization. So if you have a lot of transient effects and nonlinearities in the hull-propulsor-rudder interaction, or hull-propulsor interaction in this case, basically the moving reference frame, by invoking this idealized flow field, is washing all these out, basically, or filtering all these out. Whereas the sliding interface method is really able to capture the asymmetry in the force history, the side force history. And because the actual force magnitude might be small, but the distance from the propeller to the center of gravity is very long. So even though it's a small force, it will induce a very large yaw moment. So that's why we're seeing difference in the overshoot angles for the zigzag maneuver or turning cycles. So just as a comparison, both methods, even though there were differences, are in favorable agreement for the first overshoot angle, and then for the second and third overshoot angle, only the sliding interface method is yielding favorable results, I would say. So this was for the model scale. This was also, sea trials were available here, and this was also being performed in full scale. And here the comparison is actually even better for the CFD simulations, even though the overall conclusion is, looking at the entirety of simulations and tests that were performed, that the direct maneuvering simulation is yielding very good results. So now let's talk about costs. First of all, the time step in the moving reference approach was about 50 times larger than the one in the sliding interface method. The grid that was used was roughly 3 million cells. The paper features a discretization sensitivity study, so that was an admissible and reasonable thing to do. And it took, let's take the zigzag maneuver, it took 70 seconds basically to obtain 2 overshoot angles in this 2020 zigzag maneuver. You can see here moderate HPC resources being employed. So these 70 seconds took 1 day using the moving reference frames and 45 days using sliding interfaces. And that is only due to the fact that for the sliding interfaces, the time step was chosen according to resolving 2 degrees of propeller resolution in 1 time step. So that's a very, very small time step. So all in all, even though we get very, very good results and can study everything we want to study, that hydrodynamicists can dream of, having the CFD simulation of the maneuvering, the choice of the design criteria is actually very crucial. So let's say I just want to look at the hull and how the hull performs, and I want to do direct maneuvering simulation. So the hull propulsor rudder interaction will not be crucial actually. So then I can use the moving reference frame technique, or I can even use a virtual disk model and then basically just look at what are the turning diameters for hull number A versus B, C, D, E. Because for all of them, I use the MRF or a virtual disk model. So then I can get a maneuver in less than a day. And that's very good and anticipated to get even better as HPC resources and CFD methods like StarCCM Plus also improve. So let's just wrap this section up by this animation here has been shown before on various other platforms from Cape Horn Engineering, kindly provided. So you can see here, first of all, the global domain motion approach is being used. Of course, it's crucial to set appropriate boundary conditions. If there are any questions on that, feel free to reach out to your resources and contacts that you have as a client. This is not central to the talk today. And as already shown before, we, of course, obtain the relevant maneuverability criteria. What is the tactical diameter? What is the time to attain a certain heading angle? What is the forward speed drop? And so forth. And this is a very, very impressive animation that was created and basically underscores what is possible in terms of direct maneuvering simulation with StarCCM Plus. Okay, so let's look at some interesting things here about non-standard maneuvering simulations. So non-standard here means that we're not focused on the IMO maneuverability criteria for turning diameters, for overshoot angles. We're looking at special situations that may have caused an accident or special environmental conditions. And I want to do this by providing an example for both indirect and the direct CFD maneuvering simulation. I apologize, the PowerPoint just got in the way, but we should be back up running momentarily. So this animation here is kindly provided by Federal Waterways Engineering Research Institute in Germany, and it basically stems from the investigation of an accident, an inland waterway tanker capsized on the River Rhine. So what has been done here is a section of the River Rhine was fully modeled, and the flow velocities of this free-flowing river were computed and validated against measurements that are available. And then the tanker was fully modeled, so that the tanker was unfortunately loaded only halfway, which is very bad for stability reasons. So it included the effect of sloshing, it included the varying button topography in shallow water, and it included response to maneuvering control surfaces. So there were a lot of important answers to different questions that helped getting to the bottom of why this accident occurred. And one of it, apart from the sloshing motion causing general instability, but also giving it an unfavorable roll moment that led to the capsize, one could see that there was a relative low pressure area on the starboard side bilge, which you can see here in the left-hand side, which induced an additional roll moment and basically just was too much for this already unstable ship. And unfortunately, it capsized. So this is a very nice application for an unconventional direct maneuvering simulation. And the indirect maneuvering simulation here refers to ship-bank interactions. So a ship is sailing in close proximity to a restriction. And because of the reduced flow cross-section, there will be suction force towards the wall. And for most ships, there will be a bow-out moment. And the task was to develop a controller that will mitigate ship-bank interactions. So a simple dynamic model linear was invoked, and the coefficients were found using StarCCM+ by doing PMM tests. And then that went back to the motion equations and the implementation of the controller. And you can see here basically the ship in the upper plot, the ship is sees a suction towards the wall, and then the controller decides to lay counter rudder. So basically trying to mitigate this bow out moment. And it also decided to reduce forward speed. The suction force is proportional to a forward speed squared. So that is very intuitive what this autopilot decided. Now, talking about this link to maneuvering equations of motion and controller, we come to the last, or one of the last topics, which is interconnected maneuvering simulations. So with StarCCM+ being available in the global SimCenter software portfolio, we also have to look over this horizon and see that SimCenter AimSim provides an outstanding set of tools for different system dynamic analysis. So if we were to derive the coefficients of an arbitrary mathematical model with SimCenter StarCCM+, we can feed that into a suitable model in AimSim, and in the near future, there will be an inbuilt maneuvering module available in SimCenter AimSim. So we'll write this out from StarCCM+ as a table, read this into SimCenter AimSim, and then we can perform these standard maneuvers that we've discussed earlier on in this presentation. And the big advantage is, because that is oftentimes both in direct and indirect maneuvering simulations omitted, is we can include a very sophisticated engine model, because apparently all simulations that we've seen so far, they draw upon the assumption that the engine characteristics and propeller RPM remain constant. However, if we want to study something like maneuvering in waves, the loading of the propeller blades, torque, etc., are not constant, and we want to be as close to reality as possible and actually use a controller to stay on top of it and to model the effect of engine dynamics in the maneuvering simulation. And SimCenter AimSim can close just that gap and be linked to StarCCM+ in various ways, either for the direct CFD simulation in terms of the engine model, or we completely take coefficients found from CCM Plus into AIMSIM and then do all the maneuvering simulation if the design criteria and objective set demands that. We can do this in SimCenter AIMSIM. So talking about this, the controllers apparently or various controllers and control strategies can be implemented in SimCenter AIMSIM. So that also makes it a little more convenient as opposed to a user coding in StarCCM Plus, or some control strategies might not even be possible to model. So that is a very expedient approach in this interconnected simulation framework. And I just want to show one example here that was created by our application specialist for marine, Miles Wheeler, and Romain Nicola from the AIMSIM side. What we see here is basically a ship starting from rest, and as the bollard pull condition is being overcome, a torque controller is basically regulating RPM, and this can be used between AIMSIM and StarCCM Plus. And if you extend the engine model, this can be taken to the level of maneuvering in waves, for example. Just as a example, how CCM Plus and AIMSIM can play together for both of these applications. Now, the last thing I want to bring in here is looking even further over AIMSIM and CCM Plus horizon and bringing in SimCenter heats. That can actually be leveraged for different optimization problems in maneuvering. And one optimization problem in maneuvering, a classic one, is optimal routing. So we assume that we'll find the hydrodynamic maneuvering coefficients from CCM Plus, feed them into AIMSIM, and then we'll link to heats. And we can, for example, look at a journey from my current place of residence in the greater Boston area to my hometown in Duisburg, Germany. Actually, these days, a very socially distant journey. I think 20 knots, the aerosols will have little chance. So that is very compliant for nowadays. And then we can define different criteria. For example, if we get the weather data and the wave climate within a certain time horizon, and we want to minimize fuel consumption and minimize motion responses in a seaway, we can use AIMSIM, CCM Plus, and heats basically to solve an optimal routing problem. Now, once everybody who's familiar with the landscape of Germany knows that in Rotterdam or Hamburg, we'll have to switch to an inland vessel. So once we're on the inland vessel, we will go, let's say we stop in Rotterdam, we will go down the River Rhine and make our way home. And here we can basically feed in data from river current and traffic, and our criteria could be to minimize fuel or the shortest time to arrival. The trajectory is pretty much prescribed on a river. Last but not least, what are the facilitators for complex maneuvering simulations? So if we, for example, look at submarines, usually seagoing surface vessels in a commercial context have a spade rudder, and that can very easily be handled with sliding interfaces, etc. However, there's unconventional ship designs and also submarines. They feature X or T rudder configurations with intricate integrations into and intersections with the hull geometry. And oftentimes also the propellers are integrated into the afterbody. So here our overset zero gap method, or the general overset method, which is very robust and fast, can be used to handle the appendages for such complex scenarios. Also, if we look at special missions in maneuvering, for example, catch and release of a unmanned underwater vehicle, we can leverage both the overset grid method. Apparently there's relative motions here, and then the multi-body dynamics tools that we have in SimCenter StarCCM Plus. And let's say the mission profile of the UUV is such that it will be traveling a large distance from the the bottom of the seafloor back to the mothership. It would be very costly to have the mesh built according to the overset discretization level. So here we can use the new feature of adaptive mesh refinement to save even more computational cost and time. Here, this is an example of steady turning. So without AMR, we would have to spot this toroidal refinement zone, and AMR is basically able to dynamically adjust the background mesh based on the overset interface requirement. And with this, I want to conclude my talk. Thank you very much. I'll take questions now. We have 10 minutes left. I'd like to ask you to post the questions through the chat window. I will read them out loud to the audience and then respond at my best knowledge and capability. Thank you very much.